Yay, that's fun. Okay, at this point in the semester, because we are in week 6, next week is week 7, then there's week 8, I'm usually getting questions about how come my grade isn't calculating the same way that I calculate my grade? That's one question I get. The other question I get is, how do I improve my grade? 48 hours in advance for homework, and it's done by part. So if you're doing it on paper, make sure that you get in and get what you can, input it in, and the submissions are by column. So don't wait until you have all your homework done to put it into the system, because it does it by part. Even if you've got part A, you get the 10% bonus credit on part A, and part B will come in afterwards. Chapter 4 homework currently is due at 10 p.m. on October the 1st, which is Tuesday. Okay? So, and I will probably be at my computer some of the weekend. I do have to do some other things this weekend, but I am trying to get a lot of writing done, so I will be at my computer throughout the weekend. So if you've got a question or you need email, definitely do it. And I apologize to you guys over here in Enid. I have to be back in Tonkawa at 1 o'clock, so I will not be able to do a study session. But I'm trying to figure out a way to do a couple of study sessions, and if you've got issues, email me, okay? Email me, and we can work through some of the issues. But don't email me with, I'm just not getting it, because that doesn't help me help you. You know, you can say, I've tried, if you've tried the problem, show me your work, take a picture of it, show me your work, and then I can help you, guide you through where you may have made a logic problem. But let's talk about how the grade is calculated. So right now you've got, and I give you all of the columns, you've got a blackboard that says total. And then you've got a column that says assignment total, quiz total, exam total, then there's a lab, and a final. Now, according to the syllabus, this is worth 20%, this is worth 20%, this is worth 20%, this is worth 20%, and this is worth 20%. Your grade right now does not have your lab grade in there. And if you know what your lab grade is, you can go in and add your percentage for that lab grade and see how it's going to, in most cases, not in everybody's case, but in most cases, the lab is going to improve your grade. Okay? In most cases, the lab will improve your grade. The other thing is if you look at the assignment total, right now this morning when I looked at the assignment total, it told me that there were 271.38 points available. It tells me there's 150 points available there, there's 100 points available there, and right now we have nothing in those two. Okay? And I think it says something on the order, right now if you look up total points available, it'll say something like 871. Okay? And these points are based on the columns that are currently in Blackboard. So there is a quiz column that's in Blackboard because there's a quiz that's due next week. It's open now. It's in Blackboard. It's in Blackboard week 6. It is over forces and some vectors, kind of reinforcing some of that stuff we've been working on and starting some forces. So that quiz is in Blackboard, not in WebAssign, in Blackboard. So right now, actually there are 200 points of quiz points available, except I drop a quiz. And Blackboard is dropping a quiz, so right now it'll say there's 150 points available. But if you look at your quiz total, it's only based on 100 points. Because it's adding the quiz that's currently due into this total. Right? Your homework is doing the same thing. Right now, there's been 266.38 points that are available for homework assignments. Okay? So if you're going to calculate your grade right now, you're going to do it off of 266, off of 100, and off of 100. Now, the other total, the total that you need to be following is the percent for grade. Because this one is figuring in the weighting. This one is just totaling up the points. It has nothing to do with weighting the grade at all. It's just totaling up the points. So if you're taking your point score, dividing by another point score, it is not correct. Because it is not accounting for the weighting at all. All right? So, let's take an average. Right now, as I looked at it this morning, the average is people have 189.13 points for their assignments. That's the class average. At quiz total, right now the class average is 88 points. The class average for the exam was 70 points. So right now, if I took the class average, that's what it would do. Now because this is weighted and these two columns don't have anything in it, what Blackboard is doing right now, because I have set it up so that when things get added to these columns, this percent for grade gets calculated appropriately. Right now, Blackboard is saying that this is 33% of your grade, this is 33% of your grade, this is 33% of your grade. Right now, that's what Blackboard is doing. So if I do this, I'm going to take 0.33 times my 189.13. I'm going to take 0.33 times my 88. I'm going to take 0.33 times my 70, and this will give me a 0.23, this will give me a 0.29, and this will give me a 0.23, and you're going to add these together. And when you do that, and multiply by 100%, that will give you 75%. Now when I went and did this for everybody today, and compared it to what the weighted percent for grade is, on average, Blackboard right now, based on the rounding and everything else, is probably adding 0.5% to your grade. So even though I did this hand calculation and I get 75%, if I were to look at that in Blackboard, Blackboard would tell me it's about a 75.5% or 75.4%. So right now Blackboard is kind of boosting it just a little bit. It works itself out over the semester because we'll end up adding a lab grade, we'll end up adding a final grade, and we end up having a lot more points. So over the course of the semester, it does come closer and closer together. So everybody clear on how the grade is being calculated? Now, my biggest concern isn't the exam grade. My biggest concern are the zeros for homework and quizzes. If you have a lot of zeros in your assignment total, that's affecting your grade. If you have a lot of zeros in your quiz total, that's affecting your grade. These two parts, you've got 100% control over. Okay, you have 100% control over, and this one, you get your homework in early, you've got the opportunity for bonus points, and it actually works out over the course of the semester. You get enough bonus points that it covers 2 homework assignments. So it really does help to get that stuff in. You guys got questions over there?
There's a principle without 100.
Do what?
There's a principle without 100.
Yeah, because because right now you have 200 points worth of quizzes that are in the columns in Blackboard. It drops one, so 50 points drops away from there, so your quiz total is based out of 150. But 50 of those points are for the quiz that's currently open. So right now, if you look at your quiz total in the column, you want to do this calculation based on 100. Come next week, you'll want to do it on the 150, but right now it's based on the 100 because it's dropping one of the 3 quizzes that you already have done. Other questions? Okay. Yeah. And there's nothing I can do about the total column in Blackboard. That is a system column, and it's a pain in the tushy, and it creates confusion when you have waiting grades. All right, so where we were on Wednesday is we had set up our equilibrium problem. I'm going to move on a little bit because I want to make sure that we have covered everything that we need to cover so that you can get your homework done. So we're going to start with an inclined plane. And we kind of talked about inclined planes when we first introduced forces because I wanted to show you how to draw your diagrams on them. So if I have an inclined plane, I've got an object on my inclined plane, and it gives me this angle. We talked about drawing my force diagrams where I will get a force due to gravity, and I will have a normal force where this is perpendicular to the plane. Okay? That's perpendicular to the plane. So if I look at my object, and we talked about this before, so here's my plane, here's my normal force, here's my force due to gravity, make it so you can actually see this is my angle, and I want to get my components of my force vector of gravity in the same way as my plane system is being distributed. This is proving that that's a right angle, and this is 35 degrees. This angle would be 55 degrees, which means this angle is 35 degrees. So that shows you how this angle is equal to that angle on my inclined plane. And we actually wrote it out that this would become the force due to gravity cosine of the angle. This side becomes the force due to gravity sine of the angle. This will equal the force perpendicular, and this will equal the force parallel. So when I'm setting up my force diagrams, let's see if that focuses a little better. That's better. Is that better over there on top of? It's not as fuzzy. Okay. So when I'm drawing my free body diagrams or my force body diagrams, I can figure out those individual components of force. Which means that if I say that this has a mass of 10 kilograms, and I want to find the acceleration along the plane, okay? I want to find acceleration along the plane. I'm looking at this FG sine of the angle is going to equal mass times acceleration. And I'm disregarding friction, so there's no friction in the system. Okay, there's no friction in the system. So Fg is mass times my acceleration due to gravity, sine of the angle is equal to mass times my acceleration. I didn't even need to give you the mass. The acceleration down the inclined plane is going to be related to gravity, but it's going to be affected by how steep the plane is. And then once we know acceleration, we can do kinematic type equations. So if we start with a block at the top, and our initial velocity is equal to 0, and we say it travels a distance down my inclined plane of, let's say it's 0.1 meters, I can calculate the final velocity. V final is going to equal G sine of my angle times my distance. And if I do this, I'm going to get, and this is going to be along the plane. You get this to be positive. So I'm going to end up with 9.81 meters per second squared sine of my angle. And if we say that that angle is 35 degrees, and my distance is 0.1 meters. I plug that into the calculator. I get sine of 35 degrees times 0.1 times 9.8. That'll give me 0.56, and this is meters squared, seconds squared. Take the square root. And this gives me, so V, this is V squared, this gives me 0.75 meters per second. Now, have you guys over here done the friction experiment? Where you measured static friction and kinetic friction?
Yes.
And I know you guys over in Tonkawa have measured static friction and kinetic friction, right? Alright. Well, here's another way to do it. You guys did it in the lab, but you didn't do it this way. This is the more common way. So I'm going to take my inclined plane, and I'm going to put a box on it. Okay? And what we're doing is this. So I have this is flat. I have a calculator here, right? And static friction is going to tell me that my calculator isn't going to move as I increase the angle. So I'm increasing the angle, increasing the angle, I'm increasing the angle, I'm increasing the angle. Finally, the object moves. We can measure that angle when the object ultimately moves. Okay? So our problem says we have a block, and our block is going to have a mass of 10 kilograms. It's going to start to slip when the angle reaches 33 degrees. Okay? It's going to start to slip when the angle reaches 33 degrees. we want to find the coefficient of static friction. So I've got to put in my force diagrams. I've got my force due to gravity. I have my normal force. I have a force due to friction. I've got force due to gravity, normal force, force due to friction. I can put in my components. We know what that angle is going to be. So this side, the perpendicular side, is going to be FG cosine of my 33 degrees. This side is going to be FG sine 33 degrees. My forces are independent in the two directions. So what I'm going to do is I'm going to do the sum of the forces parallel. And I'm going to do the sum of the forces perpendicular. The trick to this problem is I am in static equilibrium until the instant it starts to slip. Okay, I'm in static equilibrium until the instant it starts to slip. So that means that I have no acceleration until after it slips. So those are going to start out as 0. So now I'm going to write my summation of forces for the case where I'm parallel. So the case where I'm parallel, and I'm going to use this direction as positive. It's going to be the mass of my block times gravity times the sine of 33 degrees minus the force due to friction. Because my force due to friction is only in the parallel direction. My force perpendicular is the, we'll do it this way. We're going to do the normal force minus mg cosine 33 degrees. And that's equal to 0. So my normal force is going to be mg cosine 33 degrees, which is going to be my 10 kilograms times my 9.8 meters per second squared. Cosine 33 degrees. I can figure in a number. And this gives me 82.2 newtons. My force due to friction is mg sine 33 degrees. And I can figure out my number there. This gives me 53.4 newtons. But we also know that my force due to friction is my coefficient of static friction times the normal force. So if I solve for my coefficient of static friction, it's going to give me my force due to friction divided by my normal force, which in this case is 53.4 divided by 82.2. Gives me 0.649. Now I'm going to show you a trick that says I didn't have to do that calculation. Okay?
Isn't it just sin theta over cos theta?
Yep. I can do it just the tangent of the angle. Because what you end up with is if I solve for the normal force, okay? Solve for the normal force. F, we said, was mg sine of my angle. My normal force was mg cosine of my angle. Divide those two, I get sine of the angle over cosine of the angle. Because mg cancels, that's my coefficient of static friction. This becomes tangent of my angle, which becomes tangent of 33 degrees, which works out to be 0.649. So we can start to include friction into the system. So let me do a kinetic friction one. And then we'll do an Atwood problem. And then we'll do my favorite. Okay. So I got a hockey puck. We always like to do hockey pucks when we're doing friction. Got a hockey puck. And my hockey puck has a mass of 0.16 kilograms. It's hit, so it has an initial velocity of 20 meters per second. And it's going to slide 1.2 times 10 to the second meters when it comes to a stop. Okay, so we're going to slide and we're going to come to a stop. We want to find the coefficient of kinetic friction. So the first thing I got to do is find acceleration. Because I'm going to need acceleration in order to work this problem. Well, you've been given the initial velocity. We know what the final velocity is. We know what the distance is. So I'm going to use v squared is equal to v naught squared plus 2a, my change in distance. This is 0. So I get v naught squared is equal to, and this is a deceleration, so because it's a deceleration, this is going to be minus 2a change in distance. Because it's going from a velocity to rest, it's a deceleration, so I'm going to have that negative in there. So that's going to allow me to do this. My acceleration is going to be v naught squared divided by 2 times the distance, which is going to give me 20 meters per second squared divided by 2 times 1.2 times 10 to the second meter. When I put all that stuff into the calculator, I get 1.67 meters per second squared. But we know it's a deceleration because we actually plugged it in here. So depending on how WebAssign asks the problem, you may have to put in a negative for the answer, but you want to make sure you understand that it's a deceleration. We have to calculate the normal force, That's just mass times gravity. That's going to be my 0.16 kilograms times 9.8 meters per second squared. That's going to give me 1.57 newtons. I do my sum of my forces, and I'm going to get mass times acceleration is going to equal my kinetic, the friction and kinetic one, which gives me a minus mu k mg, because that's my normal force. A is equal to my minus mu k g, because these g's cancel out, which is equal to minus 1.67 minus 9.8, and that's going to end up giving me 1.70. Because I have both right over separation. We'll do it that way. So it's cleaner in the notes. Yeah,
What does that capital M mean?
this capital M,
Yeah, you keep saying,
No,
no,
the,
not that one, the other one. You keep saying the word.
The mule.
mu.
Yeah, I don't know what you're saying when you say that.
Mu is just a Greek letter, and that's the coefficient of static friction, or kinetic friction. If it's K, it's kinetic friction. If it's S, it's static friction.
Okay, so it's either M, S, and K.
It's a Greek letter that looks like that. It's not an M, it's a U. It's kind of a script U.
Okay.
If you go to the symbols on the symbol keyboard, it's a Greek letter.
Okay.
Yeah, it's not an M.
I'm just writing it in, so.
No, it's not an M. And to be fair, the chemistry book that we have uses a M like this that looks an awful lot like the mu. It uses a script M, and it's actually a capital M when they're talking molar mass or something in the chemistry book. But it's a Greek letter, and actually the script, depending on which way you look at it, the script looks like that. And our book, let me see if I got one. On our book, I'm going to scroll it in. Yeah, it's not an M. It's the confusing part is it's a mu, and the pronunciation is mu, but it's a U. Yeah.
And is that different from the symbol for like micro?
No.
Okay.
No. When we use the prefix micro, we use the same mu to mean micro.
So if I see that in friction?
No, not with friction. When I'm doing micrometers, okay, so we all know distances, right? So if I see something that says micrometers and that's my distance, that means 10 to the minus 6. That means 10 to the minus 6. So if I'm putting it, I can also do microcoulombs, 10 to the minus 6 coulombs. So if I'm putting it in front of a unit, it's 10 to the minus 6. But we also use that same symbol for coefficient of static friction, or coefficient of kinetic friction. And the difference between the coefficients is one will label with an S, that's static. One will label with a K, and it's actually, this K is, a lot of times is a kappa. It's a kappa K. You'll see it both ways. Our book does it a little differently. Our book uses a script K, but if you go to another book, you may see it as a kappa K, which is the Greek letter kappa. And it's more of a blockish K.
So if that symbol is by itself, we are essentially just solving for like that as a variable. versus?
Well, in these problems, yes. Later on, no. We use mu to represent a lot of different things. You'll see mu used as other types of coefficients or other types of variables that mean certain properties. But in what we're doing right now, it's going to be the coefficient of friction. Yeah, what happens to us a lot is you'll see rho, because you've seen it in chemistry, it means density. We'll use rho to mean a few other things down the way. And part of it is you just run out of symbols after a while. And you got to reuse them. That help? You guys okay over there in Concoa? Yeah, that's the coefficient static friction. One of the things about it is, since it's a coefficient, it's a ratio, it has no units. And some poor souls are out there. Indentured servitude is alive and well. It's called graduate school. And there are some poor souls out there that all they do all day long are measure various coefficients of friction.
Why do we divide by gravity?
In this case, because right here, so I've got MA is equal to mu K mg. Masses go out there. I had the value for A. I've got G. That gives me my mu K.
And would it be the same like thought process when we're doing like the mu S and all, or is that going to be a different formula?
Well, mu S, when we did that one, that was our angle there, and it was based on how we did the summation of forces. So, this is another one of those cases where somebody always comes up and asks me, well, if you just gave me the formula, I could figure it out. Well, we had to figure out the formulas for the situation. So I can't just give you the formula. The formula is this. But then we have to know that it's equilibrium. Then we have to write out the forces that we have in the system. I can't just give you the formula. Okay. You guys good over there? Okay. Now we're going to complicate it. So I'm going to give you what's known as an Atwood device. I've got a pulley. On this side of the pulley, okay. On this side of the pulley, I have a mass. On this side of the pulley, I have another mass. And this is mass 1, this is mass 2. So let's think about this for a second. We're going to make the assumption that it's a frictionless pulley. And good for us that when usually in General Physics 1, they're always frictionless pulleys. It's not until you get to dynamics that we get mean, cruel, and wicked, and then we tell you they're not frictionless pulleys. But we're going to use it as a frictionless pulley. Now, I want you to go and think about this for a second. If mass 1 is bigger than mass 2, which way is this thing gonna go? So mass 1 is bigger than mass 2. Is this gonna go up or is it gonna go down? It's gonna go down, right? If mass 2 is bigger than mass 1, this side goes down. Now, these two things are connected by a string. And we know from experience that if I have something pulling on one end of the string and something pulling on the other end of the string, the tension in the string is going to be equal. The magnitude of the tension is going to be equal. The directions are just going to be opposite. So what I can do is I can draw two free body diagrams. So what we're going to do is we're going to say that mass 2, I'm actually going to give them numbers. Mass 2 is going to be 10 kilograms. Mass 1 is going to be 5 kilograms. So now I'm about to draw my picture. I've got tension in the rope, T. All right, I've got tension in the rope, T. In this case, because mass 1 is greater, I've got the acceleration of the system that's going over here, and I have acceleration of the system that's going there. And in both cases, I have a force due to gravity. So I'm going to do the sum of the forces about mass 1. Sum of the forces about mass 1. It's going to equal mass 1 acceleration, which is going to equal tension minus mass 1 force due to gravity. Those are my forces that I have at play around mass 1. I'm going to do the same thing for mass 2. But this time I have to put a negative sign in front of that acceleration because it's going down. I have tension going up, and I have mass 2 times gravity. So I end up with this situation of two equations, two unknowns. Two equations, two unknowns. So now you have to pick which one you're going to solve for first. So let's take this, and we're going to solve for tension first. So I'm going to have mass 1 minus, or mass 1 acceleration plus mass 1 gravity is equal to 10 for tension. And in the second one, I get tension is equal to mass 2 acceleration, oh no, gravity minus mass 2 acceleration. Those two things are equal, so I'm going to end up solving for acceleration. So I'm going to get m1 acceleration plus m1 gravity is equal to m2 gravity minus m2 acceleration. I'm going to put my accelerations on one side, I'm going to put my gravities on the other. So I'm going to get m1 acceleration plus m2 acceleration is equal to m2 gravity plus minus m1 gravity. I'm going to factor out gravity. I get m2 minus m1 gravity. Factor out acceleration. I get m1 plus m2. Acceleration then is equal to m2 minus m1 divided by M1 plus M2 gravity. If I put in my numbers, I end up with 10 minus 5 divided by 15 times 9.8 meters per second squared. So I end up with 5 divided by 15. Times 9.8. And it gives me 3.26 meters per second squared. And the fact that it's positive tells me I picked the directions correctly. Because there'll be time when you have friction in a system and you make an assumption and it doesn't work, then you end up with the opposite sign. But by virtue of the fact that I got a positive sign that said I picked my accelerations in the correct direction. Once you have acceleration, you can go back and solve for tension and be able to calculate your tension. Now, have you guys done the elevator lab yet? Anybody done the elevator lab? Okay, let's look at the elevator lab. Okay. So I've got a system here, and this is our good old fish scale. Okay, so I got my fish on the elevator, and I got the elevator, right? When it's stationary, I'm in equilibrium, and the scale is going to give me the weight of the fish. Right? If I'm in equilibrium, the sum of the forces has to equal 0. So the tension is going to equal the weight of the fish. And the tension, I'm going to write as WT, because that's what we read on the scale. We read their weight is equal to mg. Okay. If my elevator is going up, okay, mass times acceleration is going to equal tension minus mg. This becomes mass times acceleration is equal to the weight minus mg. Now this equation holds for whether I'm going up or whether I'm going down. I just haven't put any information in here about my acceleration. So if my acceleration is positive, as I start, if my acceleration is positive, the weight on the scale is going to be greater. The fish is going to look like it's heavier. And if you think about it, if I'm standing in my elevator, the elevator is actually pushing on me, I'm going to feel like I'm getting heavy. Now, if this is going up, if I'm going down, the weight on the scale is going to be less. Essentially, the elevator's falling out from under you. And if I'm using a spring scale, it's kind of easy to see how that works, because if I'm using a spring scale and I'm standing on that spring scale, the elevator is essentially compressing the spring, And that's if I'm going up. And then if I'm going down, the elevator is allowing that spring to get longer. So that's the classic elevator problem. Good? And you do have that example in your book. You have both an Atwood's problem and the elevator problem in your book. All right. We're ready. I have a penguin on a sled. I have a penguin on a sled. We're gonna pull the sled. The sled weighs 60 newtons. The penguin weighs 70 newtons. I've got a coefficient of friction. This is between the sled and the snow. Is 0.1, and the coefficient of friction between the penguin and the sled is 0.7. We want to find the maximum force that can be exerted before the penguin slides off. All right. So we got to deal with some normal forces here. I'm going to have my penguin. So this is going to be the normal force of the penguin. And I have the force of the sled. Normal force of the penguin is equal to the weight of the penguin, which is equal to 70 newtons. I have my system, which has the weight of the penguin plus the weight of the sled, which is going to be my 70 newtons plus my 60 newtons. It's going to give me 130 newtons. Everybody with me so far? Okay. When the penguin starts to slip, the force due to friction is going to be my coefficient of static friction times the normal force. But that is going to also be the mass of the penguin times my acceleration of the penguin. And that's just my regular force. So we're going to calculate the acceleration of the penguin when it starts to slip. So the acceleration of the penguin when it starts to slip is just my coefficient of static friction my normal force divided by the mass of the penguin. But my normal force, this is one of those interesting things, even though they gave it to us, there's going to be the mass of the penguin times gravity divided by the mass of the penguin. Mass of the penguin actually cancels out, and it's just going to be the coefficient of static friction times gravity, which means it's going to be 0.7 times 9.8 meters per second squared, which gives me 6.86 meters per second squared. So if I accelerate the sled at 6.86 meters per second squared, my penguin is going to fall off. My penguin is going to fall off. So now we want to look at the forces in the system. So it's going to be the summation of forces is going to look at the force that's being applied minus the force due to friction. It's got to be equal to the mass of the system times the acceleration of the system. So I'm going to rearrange for the force applied, which is what we're looking for. It's going to be the mass of the system, acceleration of the system, plus the force due to friction. And this is the mass of the system, acceleration of the system, is plus the coefficient of friction for the system times the normal force of the system. All right, the mass of the system we said was 130 newtons. So I have to divide by 9.8 because I want this to be in kilograms, so I have to figure that out. And this is meters per second squared. The acceleration is the one that I just calculated, because if I exceed that, my penguin falls off. My coefficient of friction between the sled and the snow is 0.1, and my normal force is 130 newtons. This works out to be 91 newtons. This is 13 newtons, and this is 104 newtons. So if I apply a force greater than 104 newtons, the penguin comes off the sled. We good? All right. So let's work an inclined plane problem that looks something like this. I've got a frictionless pulley. I have a mass on my inclined plane, and I have a mass hanging down. This angle is going to be 40 degrees. That mass is 5 kilograms. This mass is 10 kilograms. We're going to assume no friction. we want to find the acceleration of mass 1, and we want to find tension in the string. So let's look at this one first. I have tension, and this is 1, by the way, so this is 1 and that's 2. I have tension, I have acceleration due to gravity, the weight, and I have acceleration of the system that I'm going to indicate is in that direction. For my other one, I have tension in the string. I have the acceleration due to gravity. And my acceleration is going to go that direction. I'm going to need this one right here. That's going to be mg sine 40 degrees. I also have a normal force, but that's not going to come into play this time. So I write my summation of forces for mass 1. It's going to be mass times my acceleration. And it's going down. It's going to be mass times my gravity. And I have tension going up. Summation of forces for the second one. I'm going to have mass times acceleration. And to keep things straight, we better put our 1s by that mass. We better put 2s by this one. I have tension that's positive. I have m2 gravity sine of 40 degrees. So I now have 2 equations, 2 unknowns. So I'm going to solve for tension here. That's going to give me mg, mass 1, minus mass 1 acceleration. I'm going to plug it into there. So I'm going to get m2 acceleration is equal to m1g minus m1 acceleration minus m2g sine 40 degrees. Put that on the other side, so I get m1 plus m2 acceleration is equal to m1g minus m2g sine 40 degrees. Acceleration is now equal to m1g minus m2g sine 40 degrees divided by m1 plus m2. Plug in numbers, and I have 10 times 9.8 minus 5, 9.8 sine of 40 degrees divided by 15. I use this calculator. I get 10 times 9.8. This gives me 98 minus 5 times 9.8 times sine of 40. Minus 31.5 divided by 15. Gives me 95.9, something's not right. Oh, I know why. That number didn't look right, so I do 98 minus 31.5. Orders of operations in my calculator had the division of the 15 only in the 31, which means we have to take care of that. This looks much better. 4.43, and that's in meters per second squared. Now solve for tension. M1G minus M1A, which is going to be, M1 is 10, 9.8 minus 4.43. Gives me 53.6 newtons. Everybody good? I know brains are full, so I am going to call it. I will be back in Tonkawa this afternoon, but I'll be doing some interviews. I am around Monday and Tuesday, and over here in Enid, if you didn't get your test, I have the test.